Again, welcome to the second part of chapter 24. Basically, we will be talking today or finishing at least the capacitance. We should be also doing an example. We should be doing actually a problem from the homework. And we will also move on and probably introduce chapter 25. Again, just a reminder, the exam is still on track for October the 12th. So we should be in good shape for that. Okay. Any question about the lab? Because the lab is quite a lot of things to do, but I think it's straightforward. Does anybody have a question about that? Because we will not be meeting. Oh, I guess we will meet next Monday before actually when the lab is due. Well, if you guys don't have any question about the lab, let me remind you of what we did with chapter 24 and where we need to be. So we introduced the concept. Oh, let me open a new section. So we introduced basically the concept. Does everybody hear me well? Because for some reason I can't really hear myself correctly. Is the sound coming correct? Okay, good. Thank you. Okay, so basically, like I said, thank you, Sir Jose. So last time we introduced the concept of a capacitor, and a capacitor or capacitance in general actually is basically a, let me grab a pen in here to draw with. I like this color. So basically, a capacitor is a device that turns out to do quite few things for us. This is the representation, typical representation for it. This is not the only way the capacitor look like. So basically, what it is, you have a finite surface A with another metal that has also finite surface. Here, typically, it's the same surface A, because ultimately you would want the symmetry in here so that whatever amount of charge you remove from one, you're going to put it in the other. So you end up with a positive charge in here, Q, and in the same time, negative charge Q, okay, on the other side. This charge is distributed over an area A, therefore I have a sigma, which is simply the ratio of Q over A. So that's what the charge density in this case, Q over A. So this is how many coulombs per meter squared I have. That's what the charge density means. The unit for it is a coulomb per meter squared, okay? These two plates are separated by distance d. Typically, to allow me to do the calculations, I take d to be small, very small, compared to the typical size of what the area is, okay? In the lab, if you guys remember, we took an area of 400 millimeters squared, and in the same time, we took a distance of about 5 millimeters or something like that. So that's basically what we mean by it. As a matter of fact, I think I made a mistake in the lab, because I thought that we should take the square root. Technically, we should really take the square root because we're assuming that this is an infinite plate. In order for me to say that the electric field produced by the upper plate is pointing away from it and it's sigma over 2 epsilon naught, and the lower plate is creating an electric field also of the same magnitude, sigma over 2 epsilon naught, except that it's pointing inward towards it. Well, the outer sides, both sides of the plate, outside of the plate, the two plates, on this side, the electric field cancels because the positive plate is repelling the electric field lines, whereas the negative plate is pulling them with the same intensity, so they cancel. The same thing is happening in the plate below the negative plate, because the electric field from the negative charge distribution, namely negative sigma over 2 epsilon naught, is pulling toward the plate, whereas the positive plate, albeit it's further away, it's still pushing with the same intensity, therefore they cancel. So the electric field, in a sense, is trapped between the two plates. So that's one of the usefulness of this device, is that it traps the electric field in the region between them. As a matter of fact, in the volume between the two plates, okay? So that's one of the advantages of this device. The other advantage, of course, we're storing charges, but charges by themselves don't mean a thing. What we needed with this charger is actually energy. Nothing matters in physics unless you tally your energy, really, because that's the one that you're going to pay the bill at the end of the day for it, okay? So this is how much energy is stored in a capacitor. It turns out after we did the argument for it, we say, okay, we have already a finite charge Q, and we're building toward an ultimate charge. So we have a voltage already due to that Q. We calculate the energy, the work needed to add dQ amount of energy, and then we sum up from 0 all the way to the charge that we have. It turns out that the integration yields Q squared over 2C. Alternatively, because by definition of the capacitance, C, which is the ratio of Q over V, I can say also Q is equal to CV. So this expression can be written as 1/2 of CV squared. Both expressions are equivalent, okay? So this device also stores energy. In addition to the fact that it traps the electric field, it's a device that also can be useful for storing energy. So, and that's how much energy is in there, okay? So it stores charges, it stores energy in it, and this energy is calculated actually in joules. And we have a lot of things in there that we can talk about this device. Another thing that actually turns out to be useful, after we re-express this expression really in terms of the electric field, we found an expression for the energy density, that is the energy per unit volume, to be little u, okay, just to distinguish it from the big U, which is the total energy in joules. This U turned out to be 1/2 of epsilon naught times E squared, okay? I said this expression is going to come useful later on when we do telecommunications, when we do actually when we solve the Maxwell's equations basically in vacuum, or actually, this is actually in vacuum. And the whole discussion was actually in vacuum. We're filling the entire two plates by nothing, basically. We have no material in between them. Air behaves like vacuum because the permittivity of the air is similar to that of the vacuum, namely epsilon naught, which is 8.854 times 10 to the negative 12. Basically, in terms of light of what we know today, it's really the units of the capacitance over the units of distance, which turn out to be just farads per meter. That's another thing that we discussed last time, is the units for the capacitance are the farads. Typically, we use the microfarads because 1 farad is a huge capacitor. It's a big capacitor, okay? But the units in general are in farads. So that's basically in a nutshell what we discussed last time. We promised to go into a different situation, and we actually discussed it in the lab too, where we actually have now a different medium other than that of the vacuum between them and the usefulness of that. So I still have my capacitors, I still have a sigma in here, I still have a negative sigma in here, somehow built with a charge Q over an area A. And the same thing, the same area in here, except that the charges are negative. That's the only difference between the two plates. And the separation between the two plates is still D, okay? But instead now of having vacuum between them, I'm going to have actually a medium now that is not vacuum, another medium, an insulator. An insulator usually comes up with, it has atoms, and the atoms or molecules, and molecules can be polarized. Let me explain what that is. For example, if I take the water molecule, it's made up of an oxygen atom and 2 hydrogen atoms, okay? Under normal circumstances, the charges leave the hydrogen atoms and move closer, namely the electrons move closer towards the oxygen atoms, making this behave like I have almost 2 positive charges in here and 1 negative charge on, I'm sorry, backward, since the electrons move to, so I have 2 negative charges in here and this is positively ionized, okay? But if they are random, they cancel one another and we don't really have any problem. But now the presence of this positive charges on the top plate will reorient, I know I'm talking about water, but any medium in here will do, will reorient this molecule so that the negative side will be closer to the positive side and vice versa. Remember that discussion we had way back when we started this class actually, when I said, okay, we're going to have I'm trying to grab a piece of paper in here. This piece of paper, I don't know if you can see it or not, it's in my hand, okay? right now, it's not attracted to anything. It's a neutral charge. Okay, so what I'm going to do is grab any piece of clothing, hopefully with a little bit of, and then create charges on this insulating rod, okay, and repeat the experiment now. Oops, still not enough charges in it. You need fur really for it to work, okay? You need to grab actual electrons from the fur, because right now I'm doing it with my pens and they're not actually there. Some poorly. Okay, it's not working. It worked last time, okay? That's the trouble. That's why I ended up being actually not an experimentalist. Anyway, you guys saw the experiment that we did last time? You remember it? Yes or no? You remember what we did, or should I really go through the trouble of having this to work? Does anybody remember it from the first time? Or maybe. The paper also is kind of thick. Do you guys remember it or not? Seriously, because nobody. That's funny, Ronnie. Okay. Okay. If that pleases you, why not? Okay. Okay. Let me see now. Let me grab something that has hopefully. Okay. It grabbed, believe me. It went up a little bit. Okay. There. It worked. Okay. 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 So the point being in here, and that is a very important point I'm trying to make in here, is that the paper was neutral when I started with. And it is still neutral after I rubbed this thing in here. It's still really neutral. So it did not make any difference for the paper. Yet now it's attracted to it. And if I really go by Coulomb's law says first charge times second charge divided by the distance squared. This is still zero. This is still neutral. This one, yes, I agree with you. Now it has a charge in it. What this now is doing is inducing a charge in the paper by moving, basically reorienting the molecules of the paper in such a way that the positives will be closer to it so that it attracts it. That's basically what's going on. Albeit the negative charges do not really completely leave, they're there, so they're really weakening this force a little bit. So that's really my point in here. The paper is still neutral, but it's being attracted because there is a charge that was induced in it when I brought this one after I charged it closer from it. So that's really what the phenomenon that is also happening in the case of the so-called dielectric that I'm going to put in here. So basically, at the end of the day, negative charges will pile up in here, closer to the positive ones, and the positive ones will be closer from the negative ones. This is a negative plate. And my overall electric field, the original one, if I did not have this dielectric between them, is still sigma over epsilon naught. So this is still sigma over epsilon naught. Okay? But the fact that now I have induced charges inside the material, the non-conducting material that I have in there, I actually have created another electric field now that is induced by this electric field. So this is the other one that is induced. And that induction really depends, I'm sorry, not sigma, E. That induction really depends on the material itself. The different materials are more or less easily, you can induce charges in them versus others. So the actual electric field now is actually weakened because it's still the sum of these two, namely the field that created the induced field, and the induced field is actually opposing it, because from the clearly it's always pointing from positive to negative. So in this case, the overall electric field is somewhat weaker. So E now should be less than E naught. And I mean by E naught is when there was no actually vacuum. I mean, there was vacuum. There was no material in there other than the vacuum. So the electric field now is somewhat less than the original one, okay? Which enables me, in a sense, to put more charges, because since the electric field now is less, so is actually the voltage. The voltage, remember, V, in this case, is still E times D, okay, where D is the separation of the plates. Since now I can basically I can say that the electric field is weakened by the presence of this dielectric material between the two plates, the voltage also is less, which will allow me then to still increase the voltage further and further, putting more and more charges, and I'm fine. Do you understand the point in here? So if it is the air by itself, the air breaks, the air breaks around 3 million volts. That's when you see the lightning. That's when you see the spark, okay? So the spark, in order for you to create basically the lightning effect, with the, you need to at least reach about 3 million volts, okay? Now, since you have this dielectric between them, you can actually go higher. And that's one of the advantages of this thing, of the dielectric. The fact that you could put a material there so that to allow you to work with the same capacitor. Because technically, you could do another thing. Technically, you could get a different configuration for the capacitor. You could decrease the separation between the plates, and you will increase the capacitance. Remember, C is equal to epsilon naught times A over D. Okay, so if you're caring about all you need is just a bigger capacitor, get a smaller separation between them, or a bigger area if you can do that. So, but if you're limited in terms of space, if you're limited in terms of cost, then probably the best option then is to keep the same size, but instead introduce a dielectric between the two plates, which plays actually another role too, other than this. It separates the two plates so that they don't discharge immediately if they're in contact from one another. So it serves as actually a good technical thing for construction. It helps you construct your capacitor, and then in the same time, it increases its capacitance without having to really worry about it. Experimentally from the lab, if you guys remember, the ratio, first of all, this will result in an effective permittivity that is equal to, that is increased in this medium. So the effective permittivity is going to be epsilon naught times the properties of this material, which we call it kappa in this case, okay? So this number is only one, really technically, for the vacuum. Anywhere else, it's always greater than one. So it's only one for the vacuum. In the case of the air, as you saw from the table from the lab, it was 1.0000 something, 5 or something like that, which is very close from one. That's when we say, for example, we're doing an experiment in vacuum, air will do, is because the kappa for the air is very close from that of the vacuum. That's why it works fine. But any other material will introduce kappa that is greater than 1. So the capacitance, without really going through a lot of algebra, without going to go through a lot of different things, is going to be the same thing, except just change epsilon naught to the new value. So the capacitance will be that of the old capacitance, except that I'm replacing the value of the permittivity, epsilon naught, by epsilon. So that's basically how the expression for the capacitance now is going to look like. In your lab, you're supposed to graph C as a function of C naught, where C naught is this value. This is, I'm sorry, C as a function of kappa, where the ratio, the slope of the graph will turn out to be the capacitance in the case of the vacuum. So you start with vacuum, you calculate the capacitance, you know how much it is. That's going to be C naught. And then you yank the values of the kappa. Basically, if we're doing this in actual lab, you change the material, okay? Change the material. Put the different material, put more another material, and so on and so forth until you're satisfied with it, okay? So that's basically how you find the value of C as a function of kappa, okay? With different, this is called the relative permittivity. because it's a unitless number. Kappa, which is just the ratio of the actual permittivity of the medium versus that of the vacuum. Okay, so that's basically how this is what is relative permittivity, and it depends how well or how easily the material can be basically polarized. Okay, the more it is easily polarized, the higher this value. So that's basically how you can do it. For Teflon, it was 2.1 for different materials, and you can go on and on and on. So that's basically in a nutshell what the advantage of that is. Now you can calculate the energy now, and remember the energy was proportional to epsilon. Okay, the energy density that is. Now it's going to be kappa as much. Okay, since now you have a finite value, so the energy is going to be kappa as much. So you can store more energy for the same configuration. Okay, just by putting a material in there. Okay, so that's basically the advantage of one of the advantages of this, doing this, so that you'll have store more energy, you can put more charges, you have higher voltages. So depending on the application that you have in your circuit and the requirement for specific voltages, tolerances, or charges or discharges, depending on how much, for example, the human being will basically need for his heart to restart. So basically, if you're going to build one of those heart things, that's basically how you're going to construct a capacitor, and capacitor builds charges, bang, you put it in there, and now you have a current running through the human body, triggering motion in the muscles, all of the muscles, and one of them is the heart muscle. Hopefully it's going to restart. So that's some of the applications that you have in there. Of course, it is applied heavily in circuitry, especially for the case of capacitors near the power supply. Okay, near the chargers of your devices. You know those units, the big bulky ones that you put them. I'm trying to look for one, and I can't find anyone in here near me. Okay, so there is a couple of them down next to the plug. Okay, so those are some of the applications for these capacitors with the capacitors. Another thing that you need to think about when you're doing some of these problems is the so-called there's a word now, it's escaping me. It's the oh man. Every material can resist up to a certain voltage. I already gave you the example for the case of the vacuum. The breaking point of the vacuum, for the air is 3 million volts. Okay, this material, and it cannot go forever and ever and ever. At some point, it's going to break too. At some point, there is a discharge that's going to happen between the positive plate and the negative plate if the voltage exceeds a certain minimum amount. Okay. So that is actually another property of the materials. And again, it's listed in the tables. Let me pull chapter 15 in here. Chapter, what is it, 21 from the 15th edition. Yeah. Yeah, it's called the dielectric breakdown, okay? So, and that is the dielectric strength. That's what the voltage is. So for air, it's 3 million volts, okay? You go slightly more and you should see an electric discharge. So this is in a nutshell your chapter 24, basically. The biggest thing that you really need to remember from this chapter, and that I didn't mention when I was trying to introduce the new concept we're going to cover today, and that is if I have two capacitors or more, and if I configure them so that they are in series, then the capacitance, these are equivalent to a single capacitor, as if they are not too many, in such a way the capacitance in which they are equivalent is just the sum of all of this different inverse. First of all, you inverse, and don't forget, once you get the answer, to invert back. Okay, so you sum the inverses first. So all of the units in here are 1 over F, 1 over farads. Okay, So in order to get the actual capacitance that is equivalent to the entire thing, you have to invert it one more time. So you sum the inverses and invert back. Now, in the case where they are parallel connections, and we saw that one last time too. Where is my mouse? Okay. Great. In the case when they are in parallel, it turns out that the sum, in this case, is just of the actual capacitances. So what I mean by that is you take them side by side and you add and you connect the capacitors. And here, this configuration is extending. So you have C1, C2, C3, and so on and so forth. That turns out to be critical for us to solve some of this, especially in terms of circuits. And you'll be dealing with, as I promised, in an exam of some sort. I guarantee you, if you don't see it in exam 2, you're going to see it in the final. So this is a concept that is critical for understanding circuits, and without it, you're not going to really advance a lot, especially if you're going to take circuits later on or major in some sort of electricity and magnet. Even if you go into a mechanical engineer or any other field, as a matter of fact, you might be asked to modify a certain circuit because of certain requirements. So you might be tempted to, you might be introduced to, you might be forced into this idea just because of where you're working at. So it depends on the field. Even if you're going to be a physicist, this is something that you need to master too. Okay. I promise that we're going to go through an example from the book, unless you guys have a question. And that example is coming actually from this problem. This is problem 15 line. Okay, and I went through the basically drawing the circuit in here for you guys. This is problem 59 from the book, and I modified it slightly. I added the things that I normally ask if I'm testing a question like this one. Okay, because the circuit may be different, the configuration may be completely different. And for you guys, you really need to be ready for any kind of circuits that you might be thrown to you. This one is a kind of easy a little bit. Let me tell you why it's easy. All of the outer capacitances are the same, C1, 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 everywhere, okay? And the inner capacitors in here, the two that are branched out in here are C2 and C2. Both of them are the same also, okay? So that makes it a little bit easy. Furthermore, which simplifies this problem a lot, is the fact that the value of C1 and the value of C2, they are related. If you multiply C1 by 2/3, you're going to find C2. Basically, double C 6.9 is going to be what? 13 point something divided by 3, or divide the 6.9 by 3, which is going to be 2.3, multiplied by 2 is going to be 4.6. So this problem that you guys have in the homework, which is problem 59 from the book, okay, that's one of the homework problems, is kind of a luxury for you guys. So it's a kind of a good problem to work with. So hopefully you guys. So let's read the problem. Step 1 is that we're going to collect the information basically that we read from the problem. We're going through the process of solving this problem. So what is given to me in this problem? I need your input, guys. I need your help. I'm not going to solve it by myself.
The capacitance.
So C1 and C2 are given to me. So I know C1 is 6.9 microfarads, and C2 also is 4.6 microfarads. Okay. What else I am asked in here? What do I need to find? Anybody else?
The capacitance between A and B.
So this is basically what this looks like now. They want C equivalent. This is the point A. This is the point B. Forget this circuit. You're not looking at this circuit completely, okay? This is how it looks like for question A. You guys understand? Question A, you have a certain voltage between A and B, which is going to be given to be 420 down the road, okay? That voltage is looking at a bunch of capacitors. All of those capacitors amount to an equivalent capacitance. This is what we need to find. That's one question. Does everybody understand the question?
Yes.
Okay, very good. So the question is simply ignore this, what looks like is an awful circuit, and basically just one capacitance from the vantage point of that voltage. The second question, so that's one of the questions that we need to find. The second question was asked to do what? What am I supposed to do for the second part B? I need help in here. I know probably some of you are typing right now, but no. So what is the second question? What are we supposed to find?
What do they mean by like the three capacitors? Aren't there just C1 and C2?
Let's look at the question in here. We have to really read it, and sometimes it's worth rereading it again. Compute the charge. This is what I changed in terms of the homework problem, okay? I added the energy because typically I ask for the energy too. And the energy stored on each of the three capacitors nearest A and B. Nearest A and B, okay? When the voltage is given to be 240. So we know now the voltage VAB from this question actually is 420 volts. Okay, that's given to us. They want the three capacitors immediately next to it. So this is one. This is actually further because this one is closer and this one. So they want the charge Q1 in here. They want the charge Q2 in here. And they want the charge Q3 in here. So I labeled them as 1 and 2 and 3. Does everybody understand this part? At least the charge. And also they want something else. You guys see that? They want something else other than the charge.
Energy?
So I need U1, I need U2, and I need U3. Correct? So that's part 2. That's part B. So I have to keep track of what I am asked. So these are the questions that I am asked so far. To find C equivalent, to find Q1 and U1, Q2 and U2, and Q3 and U3. So I already translated the language that is written in the problem into the language that I have in here. Now, what's the question with the last question? What do they want? Probably should use different color for that question. Can anybody see what they are asking?
For VCD?
They want the voltage drop in here. VCD. That voltage drop. That's the last question. Okay? And they could have picked up any capacitor in the circuit, and that's what you should be expecting also in an exam or something. You could pick any point in the circuit and find it. Find the charge, find the energy, find the voltage drop between this point and this point, for example, or this point and this point. It doesn't matter which question, which part. You should be able to find all of them. Let's do first thing first. Let's find the answer to the first question because it's a key actually. Without doing the first question, we will not be able to answer any of the rest questions. So sometimes they don't tell you specifically to find the C equivalent. Even if they don't, without that step, you're not going to proceed. So as a problem solving skill for circuits, usually when you are tasked with it, try to find what is the equivalent of the entire capacitor first. In here, they were kind enough and nice enough to us to tell us to find it first. Because if they did not, we will be forced to do it anyway, or we'll be lost. We have no idea what to do. You guys understand this critical step?
Yes.
Okay, so we know from the rules before, and that actually we did last time, that is what we know now, that we have two types of configuration. 1 over C equivalent for the case of series is simply 1 over C1 plus 1 over C2 plus 1 over C3 and so on and so forth. So this is what we know. We know when they are in parallel, also when they are in parallel, that C equivalent now is C1 plus C2 plus C3. I already did 2 steps in this problem, okay? I may need something else that I know later on, but that's fine. I will add it to what I need, okay? To what we know. Do you understand? So at this point, that's probably all I need for right now. If I discover I need something else that I need to pull, I'm going to pull to solving my problem. So for right now, from the strategy that we came up with last time, we really need to find the innermost part, because this looks kind of complicated at this point. And the innermost part is this one, actually. This 3. C1 and C1 and C1. Are they in series or are they in parallel?
Series.
Since they are in series, then it's equation of the series that I need. So this is what I'm going to redraw now my circuit, okay? Remember, I have the point A and B. That is my goal. I have a C1 in here, which is still intact. I have a C2 in here, which is still intact. And I have a C1 in here, which is still intact. I have a C1 in here, which is still intact. And I have, again, a C2 in here, which is still intact. And another C1 in here, which is still intact. Now this 3, I'm going to replace them by their C equivalent. Okay? So these 3 are no longer going to be C1, C2, C3, C1, 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 but they're going to have a new equivalent, which I'm going to call CEQ1. And I need to find what that CEQ1 using the equation for the series. So 1 over CEQ1 is equal to 1 over C1 plus 1 over C1 plus 1 over C1. Okay, and the justification for it, why I can do that? Because they're in series. So since they're in series, okay, since they are in series, as I am solving, I'm justifying my steps. You understand? So I'm doing 2 steps at this point: solving and justification. Okay. Well, is it C2? There is no C2 in here. All of them are C1. Do you guys see that? All the 3 capacitors are C1s in here. C1, 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 C1. So 1 over C1 plus 1 over C2 plus 1 over C1 plus 1 over C1. The common denominator is C1, so this is a simple algebraic operation that gives me 3 over C1. Okay. At this point, it's an algebra. Okay. If it's a multi-step algebra, I probably need to justify it from the algebra. At this point, there is really no need to justify it. The common denominator is clearly C1, and the numerator adds to 1 plus 1 plus 1, which is 3. In here, just by inverting, and again, I don't really need to state that, the C equivalent 1 is going to be C1 over 3. Okay? C1 over 3. So I found C equivalent 1. So this one actually is a C1 over 3 numerically now. I found it. I can plug in the number instead of 6.9 now. If you're curious trying to find it, it's 2.3 microfarads. Okay. For this specific problem, I don't really need to. Technically, probably I should. As a matter of fact, for this problem, I already noted the fact that C2 is 2/3 of C1. Okay. I already know numerically that C2 in this specific problem. Otherwise, you're going to plug in the numbers, okay? C2 is actually 1 over, means 2/3 of a C1. This is not true all the time. It's only for this problem. So I really don't care about this one in here to have it as some sort of a general rule or something like that. The numbers that they gave me for this problem work out this way. But otherwise, they're not, it's not always guaranteed that you're going to find that number. The reason why I'm saying that is because now I want to ask, what is the most inner part in here? You guys see that now I have to deal with this too and find their equivalent? Yes?
Yep.
And they are in series or in parallel?
Parallel.
They are in parallel, yes. Everybody else, please participate in this process because it's... So, I'm going to come back in here to the bottom in here and try to draw in here with a different color. So, this is where we are right now. So, I'm going to replace this 2 by their equivalent. So, I still have C1, I still have C1, I still have C2, and I'm sorry, this C2, and I still have C1 and C1, but the C2 and the C equivalent 1 are going to be C equivalent 2 now. So now we're reduce the circuit now further. I know I'm taking step by step, but I really want you guys to see it, okay, at least once. So I have a C1, I have a C1, and I now have a C equivalent 2, and I still have a C1 in here, C1, C1, and I have a C2 now in here, and I have a C1. So this C equivalent is between parallels, and per the parallel circuits, the C equivalent is just the sum of the two, that's it. So C equivalent 2 is simply C equivalent 1 plus C2, okay? Numerically, for this specific problem, this will turn out to be exactly C1. This will add up in this particular problem, not always, not always. For problem 59 only. For 59 only. C1, I'm sorry, C equivalent, which is actually C1 over 3, and C2, which is 2/3 of a C1. When you add them up, they're going to add up to C1, okay? In other words, the 4.6 plus the 2.3 is exactly 6.9, which is our question of the day today. This is only true for problem 59 of the homework, okay? So the fact that this C equivalent in here works this way is only for problem 59, okay? So please do not generalize this one. I want you to really have that emphasized on. So this is the discussion today, okay? The reason why this one added up to the C equivalent 1 and this C2 added up to another C1 is because of this setup for this problem 59. Does everybody understand the question and the answer? I don't want you to really be confused with this step with another problem, because other problems we might not have that luxury. Do you guys understand? Yes or no? CEQ2 is C1 only in problem 59. So do not, of this homework, do not make any kind of generalization in here somewhere else, okay? Because the numbers work this way. So if you're given another assignment where the C's are completely different, do not plug in C1. You might end up with a different value. You guys understand what the task is today? Okay, thank you, Sebastian. So please do not confuse this part, okay? I know when I was looking at this problem, I was going, oh boy, hopefully they will not remember that this is some sort of another hidden rule or something, okay? Just the numbers, the way they work themselves in this problem. So this is where we are right now, as if the other part did not exist at all. This is this is why I'm warning in here, okay? This is the original circuit, okay? As if C1, C2, C1, and C2, all of these guys are just C1. And that is because of this problem, not of anything else, okay? Just in this specific problem, okay? Don't get it somewhere else. This idea only, somehow, the person who puts the problem 59 seems like he was really enjoying himself. He put the numbers in such a way this worked out correct. Okay. Now, so this is where we are right now. We are at C1, 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 and C2 in between them. Again, C1 and C1 and C1. Right now, they are actually in series. We already did this step before. So this is going to be a new capacitance, which is C equivalent 3. Numerically speaking, because they are going to be all three of them in the series, is going to be just like the first one we did, C1 over 3. Okay? So that's basically how this ended up being. Okay? This is for this problem and this problem only, not all the way, or not always. Okay? Again, the C equivalent for this 3, C equivalent 3 now, we are at C EQ3. We're reducing our circuit further and further. This is how the circuit now look like. We still have this C1, we still have the C2, we still have the C1, and replace everything on the right-hand side just by their C equivalent 3. So now, we have a C1, we have a C2, and we have subbed everything by C equivalent 3 now, and removed everything from the picture except this CEQ3, and we still have our C1 just before going back into point B. Okay, so this is how the circuit look like now. I already did this one, which is C1 over 3, just for this problem. And this one is already 2/3 of a C1. And these two are in series again, I mean, they're in parallel. Therefore, the equivalent for this specific problem and this specific problem only, again, is going to be C1. Because 2/3 plus 1/3 is going to be just a C1. So C equivalent 4 now, CEQ4, is simply another C1. This is dangerous. This problem 59 might lull you into thinking that all problems are going to reduce this simple. This is not true. This is far from the truth, okay? So this problem is kind of a trap. Hopefully you guys don't fall in it, okay? So this is basically where we are right now with the CEQ3. So we still have our starting point. Now we have a C1. We have a C1 that is actually, that is coming from CEQ4. It turns out numerically only to be equal to C1. And now I have another C1, which is part of the inherent problem, the real problem. And they are now in what configuration, series or parallel? Between A and B.
Series.
They're in series, and they're all C1s. So the C equivalent, which is now everything, after I get rid of this one and basically put my C equivalent in here, is just going to be 1 over C1 plus 1 over C1 plus 1 over C1. Invert that is going to be C1 over 3. So it's 2.4, I'm sorry, 2.3 microfarads. Simple. In a real circuit, and again, I cannot really emphasize enough, you will have different numbers, and you really have to do this algebra more carefully than what we're doing right now. Does everybody understand this prompt for today's discussion? Yes. It worked out this problem this way only for this problem 59. Yes or no? Yes, do you understand that it really requires a lot of algebra for other steps, not necessarily this one? Come on, guys. Okay, thank you, Alex. So basically, this problem only worked out itself this simple because of the fact that the way it was set up. Okay. Now we have already answered part 1 because C equivalent is actually 2.3 microfarads because 6.9 divided by 3 is 2.3. Okay. What's the second question? The second question was to find the charge on Q1, the charge on this Q2 and the charge on Q3. Remember, if I find the charges, I already found the energies because the energies are given by that expression. 1 over 2 times the charge squared divided by C. And since the C's are given, so we can find the energies quickly after I find the charges. So we're going to do that both in the same time, okay? So we're going to find the charges first. First of all, the entire charge that is basically sitting on the entire equivalent capacitor is given by the voltage VAB, because from this structure, I have VAB, this is B, and this is A. I have the VAB in here, VAB, which is equal to basically Q divided by C equivalent, okay? Or Q equals to the C equivalent times VAB. So that's basically an answer to that. So Q total now, okay, is going to be equal to VAB times C equivalent. That's why this step is necessary. You needed really to find the C equivalent to find how much really charge was drained from that voltage. How much do you have really sitting on here? There will be a positive Q total in here, and there will be a negative Q total in the bottom. Okay, so that's basically what we're looking for. So in this case, the Q total is going to be 420 volts times 2.3 microfarads. Okay, so 420 times, I don't have my mathematics. Okay, let me plug in my device before this dies. So 420 times 2.3, according to the calculator, is 966 microfarads. Okay, 966 microfarads. So I'm going to leave it as is. Okay, so Q total, I'm sorry, not microfarad, micro coulombs. 966 microcoulombs. Okay, because the farad and the volt are actually coulomb, and the micro didn't tangle with it. I didn't mess with it. So that's the answer for the total charge. But that's not what I was asked. I was asked for the charge that is sitting on this capacitor. Okay, C1. So let's try to think through now in here, since we found what the C equivalent in here. So let's go back into our circuit to see how it looks like. We have 420 volts between point B and point A. And we have 966 microcoulombs on one side, micro C on one side. And we have negative 966 microcoulombs on the other. So here is my negative 966. Here is one my positive 966. If I have a positive in here, I have a negative in here with the same value. That is basically what the whole purpose of the capacitor is. So the charge Q1 is already known to be 966. So that's Q1, and that is actually Q3 also. Okay, this is positive, that's negative, that's fine. So in this case, I'm assuming that B, actually, the way I structured it right now, this is where the 420, this is the higher potential, okay? Assume that this is 420 is pointing backward, okay? Otherwise, the signs will be flipped. So Q1 is equal to 966 microcoulombs, which means U1 is equal to 1 over 2 Q1 squared divided by C1, okay? And here is what I need to plug in the numbers. I have 1/2 times Q1 squared, which is 966 squared, divided by C1, which is 6.9. Yeah, 6.9. And I have a micro coulomb squared over a microfarad, which is going to be a microjoule. Okay, so the number might be big, so I might need to do some conversions, but that's fine. It's no big deal, really. So I have 966 squared, okay, divided by 2 times 6.9. Okay. So the answer is 67,620 microjoules, or 0.067 joules actually. Okay. I multiplied it already by a millionth or something like that. So that answers that, okay? And that should be the same answer for the Q3. Q3 actually is the same charge as Q1. And U3 is actually the same energy as U1. Because they have the same capacitance, okay? The problem is not there. The problem is going to be this guy, C2. Okay? That's where the problem is going to be. This charge Q2 and the energy there. For that, I need to get to a step in the calculation that we did when we reduced the circuit just to where that Q2 is in parallel with something else, okay? And that is the situation, okay? We have here CEQ2, which turned out to be C1 over 3, and this, where is it? Another way of doing this one is finding the voltage first, okay? I know the question is asking for the voltage last. We should be able to get the voltage now. Once we get the voltage, we should be able to get the answer to that question. So in this case, and sometimes it's true also to do this one backward, and let me tell you the rationale. You could do it. You could still do the problem the way it is, okay? But it's a little bit kind of a long way of doing it, but there is a shorter way of doing it. Since I know it's 420 volts between points A and B, okay? If I can find the voltage between A and C, if I can find the voltage between B and D, then I know what the voltage between C and D. And let me explain why that is. And that is actually the question that Faraz asked last time when we were doing the lecture, okay? So let me inject in here the voltage between A and B and see how that works. The voltage between A and B is actually VB minus VA, albeit this is a negative number, it doesn't matter. It's going to be VB minus VC, okay, plus VC minus VD, VD, plus VD minus VB. Does anybody object on this operation? I'm sorry, VA, the last one is VA. Okay, let me correct all of this, okay, because this is not the logic that I want to do. Okay, so let's write it step by step. VB minus, because next to B actually there is D, not C the way I did it initially. VB minus VD first, plus VD minus VC, okay, plus VC minus VA. Does anybody object? Let me put this one in the big screen so that everybody can see. At least it should give me. You guys see the expression now? VA, VB, VAB. I'm saying it's VB minus VA. That's correct. That's what the difference in potential between A and B is. It's the difference in potential between B and D plus the difference in potential between D and C plus the difference in potential between C and A. Do you remember this question for us? From last time? From Monday?
Yes. Yes.
That is the same thing, except earlier on Monday, we only had one middle point between the two. Now I have actually two middle points, which are C and D, okay? At some point, we're asked about this specific voltage. That's the last question, okay? We're supposed to find what this voltage is. That's question 3 of this problem. Since I know this one is 420 volt, if I can find what this one is, and if I can find what the last one is, then I should find what that voltage is. If I know what that voltage is, I will answer the question about the charge and also the capacitor. Does everybody understand the plan of action now of how to tackle this question? So I reverted now, and I'm going to answer the last question first, trying to find what this voltage is. If I find that voltage, then I'm going to just apply the formula for the capacitance and the charge. The charge is equal to the capacitor, which is C2, times the voltage. And if I find the charge, then I have found actually the energy too. Okay? Remember, the overall voltage is 420 volts. So no matter what happened, this voltage cannot be more than 420 volts. Okay? It has to be less. So, since I already know what the charge is sitting on this capacitor, which is just the Q total, and I know what the capacitance is, which is C1. So all I have to do is multiply Q1 by C1. Q total by C1, basically. So it's going to be, what is it? No, the voltage is Q divided by, not added, I'm sorry. It's Q divided by. So the Q total is 966 microcoulombs. And the capacitance in this case is C1. C1 is 6.9 microfarads. You see the advantage of leaving the micros intact? You don't have to worry about them now in doing the calculation. Actually, all you have to do is just divide by them. Divide 966 divided by 6.9. I don't have a calculator available right now because I'm in the full. No, I can. I'm sorry. So I have 966 divided by 6.9. And the answer is 140 volts. Does everybody find 140 volts? Yes? Because the micros cancel, so the answer is going to be straight out in volts. Does this fit the bill at least? Is this wrong? 140 volts, is this wrong? May not be correct, but is it wrong? In other words, is it more than 420 volts? Is it
No.
more than? So at least we know it's not wrong. It doesn't mean that we know it's correct. If it were more than 420 volts, which is the overall voltage, then we have a serious problem. We have somehow a source of energy that we didn't account for to begin with. This one also must be 140 volts because they are the same thing. The same capacitance, which is 6. This is C1 also, and the same charge. So this also should be 140 volt. So I'm left with the middle one, which should be also 140 volt. Because 420 minus 280 is 140 also. Okay? So we know now the answer to the last question. What is the voltage VDA, VDC or VCD? It's 420 volt. Okay? So that's the last question. VCD is 140 volts. Okay? There is another way to check. We really need to check that it is, but at least from this one, we use the C equivalent 4, I think, the one that gave us the value to check on it to see if it is or not, okay? But for right now, this is the value that we have for the voltage there. That's the last question. Now we need to go back to the question 2. Since we know the voltage, and we're asked to find what the charge is on C2, well, in this case, the charge Q2 is equal to C2 times the VCD now, okay? That is the voltage between its ends. Yet it's true, it's not just between its ends, it's between its ends and whatever is on the other side also. But that's irrelevant as far as it's concerned. That's the only voltage it sees between here and here. This voltage of 140 volts also sits between this side. But as far as this capacitor, that is 140 volt, okay? So that's the voltage that I need to write for that expression. And the capacitance in this case is 4.6. Is it 4.6? So I need to multiply 4.6 times 140 volts. Okay? To 4.6 microfarads times 140 volts. Okay? I have to be careful with my units because the answer should be in microcoulombs. So I have 4.6 times 140, and the answer is 644 microcoulombs. Okay. So remember, I have 966 that was drained from the top drawer, basically from the top of the capacitor, from the top of the voltage, from whatever source, battery, for example. I have 966 sitting on here, which means negative 966 in here. This negative 966 was split between this side and this one. 644 went already here. So I know how much went to this C1 if somebody asks me how much is went to C1. Because this charge of 966, 644 of it went to this capacitor. I just calculated it. So the difference is what went into C1. Obviously, the one that I find in here is split between C2 and this C1. So if I find what this one is, I can find what the capacitor on C2 is, and I can find what this capacitor charge on that capacitor, and the energies and the whole thing. So let me answer the last part of the question, because we needed to actually find the energy too. We're not just asking for the charge. The energy is simple in this case. U2 is 1 over 2C2 times 644, which is Q2 squared. So the numerically speaking, it's 1 over 2 times 4.6 microfarads, and I have in here 644 squared microcoulomb squared. Okay, so again, I'm going to plug in the numbers in here and see how that's going to look like on my calculator. 644 squared divided by, open parentheses, 2 times 4.6, close the parentheses. I have 45,080 microjoules, or 0.045 joules. Okay, so that's the answer to the last question here. 0.045. There is a 080, and the same thing with the other one. I'm not really counting it joules. So that's how much energy is actually stored in this capacitor, in these capacitors. Does everybody understand the steps on how to solve this kind of problems? I recommend that you go through, since it's part of your homework anyway, you're supposed to sub these numbers and going through that and everything else. Part of the discussion, I already hinted to it, that you could have, the fact that 966 microcoulombs was split. Part of it went to the 644, so I know the difference is gone to the C1. I can actually calculate the difference in here and say this is how much went to C1, and apparently that one is split between the other two. So that's basically how much it is. If I am curious trying to find how much energy was taken from the whole battery, then it's another story. Then I'm going to go and calculate all the energies, or at least with the C equivalent, and find that it should be equal to the C equivalent. So that's really part of the discussion that I should have in here, okay? It's not just, does it make sense? It makes sense in a sense. For example, the 140 volt that we found for VCD, it should be less than 420. So yes, it makes sense. At least we know we were not wrong. Doesn't mean that we were right. So this is kind of discussions that I expect to see, hopefully, trying to enrich the topic, trying to go beyond the question that was asked, to show really that you understand. I know some of you probably have access to solutions from some other manuals, or you can ask somebody else to give you the solution and you already have the solution. But if you don't show me you understand the solution, you're going to struggle actually during an exam time or testing times, because you don't really understand what that solution that was handed to you, what it means, on how to use it and how to understand it and things like that. Okay. Is everybody with me so far or not? Okay. So I'm really hoping that you guys will take this problem and try to learn from it on how to tackle problems in general, albeit this is kind of simple problem a little bit, numerically that is. Logically, it's not. Logically, it has a lot of structure in it. It has a lot of basically questions in it. And you needed to think through to find them. Numerically, plugging the numbers was kind of easy. You really don't need a fancy calculator or anything like that. Okay. There is another problem, I think, part of the homework set, and that is you take, I don't remember the exact details of it, but basically you have capacitors that they are in series. You charge them. You put them under certain voltage. Now they are charged. You remove the battery. So you know how much energy now is stored in each and every one of them. So you know how much energy you have overall. You take those capacitors, being very careful not to discharge them or to lose any charges in them. You change them from a series configuration just to a parallel configuration. And you recalculate the charges on them, because the charges now have to reduce themselves. The voltage drops are the same everywhere. So there is an exchange of charges. Give me that, I give you this, and so on and so forth, until now they settle into a certain configuration. And now you recalculate the energy again. And you find that the energy is not the same as before. There was a loss of energy. So where did the energy go to? That was not a question asked in the problem, by the way, of the homework. But I want you to think about that problem as you're doing it, as you find a different value for the energy. Part of your discussion there is trying to think, where did the energy go to? Because you have, let's say, for example, you started with 10 joules when they were in series. Now just change the configuration, and now you have 8 joules left in the system. You didn't do anything. All you did was take this capacitor that was sitting in here next to the other one, next to the other one. You wore insulating gloves to make sure that you don't discharge them by mistake. You took this capacitor and put it on the other side, took the third one and put it on top, and you connected the wires now. You connected them, all three of them. You take your multimeter and measure the charges. You find new charges that correspond to the correct configuration now that they are in parallel. But the energy is less. So I want you to be part of the discussion, is trying to think, where did the energy go? Okay. We should really explain something like this one. Okay. Obviously, it's probably during the transition, something was dropped. When you make the transition between these things, you might feel some effects there. And that's basically where the energy is gone. So, but you need to think about that. So that's basically, in a nutshell, some of the problems that you have for the homework. We still have about 15 minutes, 12 minutes to introduce the next chapter, unless you guys have a question about this chapter. No? So let's introduce the next chapter. And okay, how do I exit the full? Okay, here it is. Okay, go back into my slides. By the way, I mean, you think that this circuit is probably complicated. Wait until you see kind of circuits that you'll be dealing with. And this is even if you are not an electrical or an electronic engineer. So this is something that is, this is actually a power supply configuration. It's just picked on the net. You see how many capacitors it has? It has this one in here. It has this one in here. Next to every one of these transistors in here, these are transistors, by the way, there is a capacitor, okay? And in here, there is another one. These are resistors in here. These are diodes in here. Another diode in here. What is it? This one, whatchamacallit, a transistor. This is the power supply in here. This is basically a transformer, which is part of the things that we're going to be learning in this class. This is a regulator that basically regulates. This is a bunch of diodes that actually fix the current in one direction and one direction only. This is another transistor in here. This is T1, that's T2. This is a complicated circuit. I mean, so if you think that what you did is a little bit complicated, it's not near anywhere where it could be. This is actually an integrated circuit in here that you guys are looking at. This is a whole logic by itself, including this logical basically devices in here that add current or subtract for logical operations. So this is complicated stuff, isn't it? But capacitors are everywhere. This is a 1 microfarad, which is kind of big. This is 0.1 microfarads. This is 0.1 microfarad, 0.01 microfarads. They're even tinier, okay? So there are all kinds of devices. Of course, there's a ground all around in here. But again, this is just a picture or graphics for one of the power supplies. And in here, you have the series, the parallel configuration in here, depending on the current and how much it's flowing, which one will, where it goes. And you have, of course, series configurations all about too. I mean, it's not Here are three stuff in series in here with this variable resistor in here, okay? So that's basically how these things are. Just wanted for fun to give you a picture of how these things look like, okay? So this is in a nutshell chapter 24. We still have about 10 minutes. Let me introduce chapter 25 for you guys and then we'll call it a day. So what was the question of the day? About this problem 59, and it's kind of luxury, okay, to have the data the way it is. Okay, so chapter 25 is basically about resistors. Remember, we said conductors do not have a charges inside, and they don't, okay? They don't have, if you sprinkle charges on a conductor, they all go to the surface. They don't stay inside. If you go today to Home Depot and you would want to buy, for example, conduit for your water, for the water supply there in your house, for example, or your place or wherever you are, and you tell them, okay, I want a conduit for the water, and they tell you, okay, here is one, depending on how much diameter you would want it for, depending on how much length, they will cut it for you, they will give it to you, here it is. Remember, when you carry it from Home Depot all the way home, it does not have water. It does not come with water. You're supposed to get the water from the water company, okay? But if you tell them in the same time that you need actually wires for your electrical circuits too, they will give you the wire. They will cut you again how much the gauge for it, how big is your cross section basically, and how long it is, and specifications if there are any, and things like that. You tell them all of your requirements, and they cut one for you or give you one that is already ready for you to go. That wire, unlike the conduit for the wire for the water, comes with the charges already in it. Comes with the water already part of it too. Okay. So what is the power company doing versus what the water company is doing? The power company does not provide you with electrons, does not provide you with charges, it provides you with the difference in potential, that's all. So if I have this wire, okay, this is the one I grabbed today from Home Depot, for example. It has already charges ready to move, okay? And the power company, what it does in here, it provides the voltage difference between this end and that end, okay? So that the charges start moving. The electrons actually move in one way, the current is moving in the opposite direction. What we're going to be doing in chapter 25 actually, is calculating the current that flows inside the wire, finding how that current depends on the voltage. There is a voltage across the wire in here, V, and we're going to find the expression for the voltage as a function of I. The expression that we're aiming at is the so-called Ohm's law, and this is how this relationship will look like at the end of the day. V equals to Ri. That is one of the fundamental laws of electricity that we're going to discover. This is called Ohm's law. So this is really the ending thing, the purpose of this chapter that we have in there. So again, this is your question 2 for the day, okay? The discussion item 2 is that the target for next chapter is Ohm's law, okay? So what is the purpose? Which is a big deal, okay? The reason why I'm emphasizing on this one is because I want you guys to be ready for it. At least I know the words right now. Ohm's law relates current and voltage drops, currents and voltage drops in a conductor. I mean, mathematically, if you really want to write it mathematically, V equals to Ri. Okay, so that is your question 2 of the day. So there are 2 items for today. The first one, the fact that we have dealt with problem 59 and went through it step by step, and we discovered all the answers to those questions plus some. And in a sense, we really did not really struggle with it, at least numerically speaking, because of the fact that the numbers turned out to be easy for that problem because of the way that it was set up. Okay. The second question is and that's why I wanted to emphasize that last point so that you don't be tempted to think that this is some sort of a rule. That's an exception, not a rule. Okay. And the other one also in here is Ohm's law, because it's going to be at the heart of your exam 2 is this law, okay? Ohm's law, which we're going to derive actually on Monday, and we're going to do labs on it on Monday. So this is going to be our big focus in terms of the second exam, in addition to what we saw already from examples from problem 59, and there was a few other problems I didn't discuss in here in terms of capacitors. And at some point we're going to combine capacitor and resistors. This is a resistor actually. We're going to have a situation where we build the charge in a capacitor, and then we get rid of the charge of the capacitor. We charge the capacitor and discharge the capacitor. That is going to be a big deal in terms of chapter actually 26. Okay, so that's basically how this thing is shaping up to be. Any questions before we call it a day? I have a question for you guys. Does this sound a lot? Is this overwhelming a little bit?
A little bit.
Yeah. Yeah, I think my recommendation for you guys, I mean, honestly, I think when I took this stuff first time, of course, I found it kind of a mountain to climb. Okay. So I will be honest with you guys. The only way to remedy that is to start right away in your homework problems. If you discover difficulty with it, if you don't understand, for example, a step, or for example, it's kind of fuzzy, please do ask in the discussion, and let's get these things moving, because it might be kind of fuzzy for you, the whole thing in here, but it might be just an area, for example, of concern for you. And if that's clarified, maybe a lot of steps later on will be easy. And if you ask that question, chances are everybody else will be very grateful for what you asked, because they were actually struggling with the same thing too. So the first person who goes first usually is actually the person with the most basically courage to ask that question, and it helps everybody. So my recommendation for you is to start right away in the homework problems. Do not let things accumulate toward the end where they become basically an unmanageable task. You don't want that. Okay. You want them to be really as smooth as possible, because like I said, I mean, things are piling up. Next week we'll do resistors, Ohm's law, then after that we do circuits and things like that, and then we'll look back on today and see that this stuff that we're doing today is kind of basically elementary stuff. So I really want you to get started on it. Ask the questions. I don't mind going one-on-one with any one of you, and if it benefits everybody, I'm going to record it for the benefit of everybody. Yes? You promised that you would do, guys?
Yeah, I'll try.
Okay, please, yes. Okay, so did you guys also receive? Let me stop the recording right now because we're done with the business. We're still in class, okay?